Namaskar, my dear friends. So we have been seeing the intelligent power module designs. What we'll do is we'll try to understand all about IPM designs with a low power device which is up to 3 ampere, 600 volt and three phase inverter bridge IGBT. Okay. So this is a device from Slim Nano series which is from STM, and the device name is STGIPN3H60AT. So what we can understand is it has the applications of, let us say, in home and professional appliances. So basically it will be used in dishwashers, dryers. We have some kitchen hoods, we have refrigerators and fridges, and we have washing machines. So only, or not on washing machines, some clothes washers or something like that which is having a small power of that can be utilized. Okay. So these were the applications for this particular small IPM that we are going to design, and we will understand through this particular like design and detail that what are the things that we need to take care of while designing with a IPM system. Okay. So let's open the data sheet for this particular device. So as we can see, this is a particular data sheet coming from STMicroelectronics. Okay, and it is having slim nano IPM with 3 ampere continuous current rating and 600 volt of IGBTs with 3 phase inverter bridge IGBT. Some of the features if we try to understand. So as I told you already, 3 ampere and 600 volt. Okay, now it has been optimized for low electromagnetic interference. So electromagnetic interference or EMIMC issues will be very small, very minimal. Okay, now it has voltage collector to emitter saturation voltage having negative temperature coefficients. Okay, negative temperature coefficients means with increase in temperature the value will be lower. Okay, this is how. And it has a capability of working with 3.3 volt as well as 5 volt logics and 15 volt supply as well. Coming back to other features, it has under voltage lockout capabilities. It has internal bootstrap diode. It has interlocking function. It has been optimized for very easy board layout, and the biggest advantage, it has internal 85 kilo ohm NTC, that is negative temperature coefficient thermistor for temperature control units. Okay, and as we can see very clearly, we have the application of this particular IC which is having three-phase induction motors. It can be used in dishwashers, fans. It can also be used in PM, SM or BLDC motor control, and as well as it can be utilized in our refrigerators and fridges. Okay. With this, we'll try to understand some more items what we generally look into while designing with like IPM systems. So basically, this data sheet we'll try to understand one by one all those parameters. So moving to the next pages, as we can see, we have the internal diagram. This is also nothing but a block diagram, we can say. So block diagram can tell you like what are the different blocks that is there inside the IC. So regardless of any IPM, if you see, you will be definitely getting like yeah, I mean VCC W, VCC V, and VCC U, VW. Okay, so there will be one more VCC U. So that is nothing but low voltage power supply input that will be used for your gate driver MOSFETs. And we have logic inputs. These are nothing but PWMs. That is your W, and that is your V, and that is one more U. Okay, so these are PWM inputs. Okay, it can be told as PWM directly for high side and low side drives. Okay, so these are the PWM pair that will be coming in. That is nothing but the logic supply that is coming from the microcontrollers. Okay. So as you can see inside the IC, we have the gate driver. So there will be three gate driver high side and three more gate driver will be low side. So as you can see, this is actually integrated inside one IC itself, high side as well as low side both. Generally in high current IPMs, these will be separate. And these are the six MOS IGBTs, like one pair, two pair, and one more pair which is going to be down, which is three pairs of IPMs that is used for a three-phase drive or three-phase switching. Now coming back to the UVW phase, so we have outputs as you can see. Where is that? We have U out, and then we will be having V out, and then we will be having W out. So this will be three pins which will be used for our motor drive UVW. Understood? Similar to that, we have NW, NV, and NU. These are lower side power supply. So this is nothing but going to get connected with our shunt resistor that will be used for our current monitoring. And main is the power supply which will be going into this, which is having high voltage DC. Let's say 300 volt. It will be supplied at this particular point. So this is complete block diagram of this particular IC. There are some other pins as well. We will see during our like design phase, but let's get into the pin description. So as you can see, we have the pin numbering, we have the symbol that is written in the pin names, and we have the complete description. So we can see that it is a pin number 1 is ground, pin number 2 is T, which is NTC thermistor terminal, which will be used for our temperature control, and seeing out, watching out like what is the temperature based on the IC working. So as IC starts working with time, it will get heated up, and this is how the temperature gets increases. Okay. We have VCCW, that is going to be low voltage power supply W phase. Similar to that, we have H in W, that is high side logic input for W phase, and LIN W, that is low side logic input for W phase. So basically it is nothing but this is going to be, let us say, 15 volt, and these two will be my PWM, which will be in complementary phase. Okay, so complementary phase. So similar to this, like high side low side W, there will be high side low side V and high side low side U. So these are the 6 PWMs that will be given to the IPM to drive the gate driver. Okay. As a gate driver which will be used to drive the MOSFETs. Coming back to other part, we have one more NTC terminal which can be used for our temperature sensor terminals. So similar to this one, this is also T, one more T is here. So we have several T terminals, okay, T parts that we can see. So T pins are there, 1, 2, and this 3. Coming back to other parts, we have already seen VCC, W, V, and U. Let's talk about bootstrap voltage for U phase, V phase, and W phase. So basically there will be a capacitor that will be connected to the bootstrap pin and to the VCC pin. Okay, so VCCU, it will get connected with boot U. Next is we have P, which is our positive DC input. So that will be taking up the high voltage input from our either battery, or maybe one AC to DC converter will be there. In that, after bridge rectifier, the voltage is rectified voltage. So this rectified voltage only comes as the input to the DC input. You don't have to go ahead after the DC, because that will be coming very low voltage, which can be used for our control logic purpose. Okay. Now we have U, V, and W. That will be U phase, V phase, and W phase for our motor drive. That is 3-phase motor drive. That's all. And then coming back to the last one, which is having like NU, NV, and NW. So this is nothing but negative DC input for U phase, negative DC input for V phase, and negative input DC input for W phase. So that is nothing but going to get connected with 3 shunt resistors, which will get like monitored in U phase, V phase, and W phase. What is the current that is being consumed in each phase? Okay. And that's the place where we try to merge all these 3 shunts into one shunt resistor, and we try to design with lower cost systems. Moving on to the next page, as you can see very clearly, it is showing the pin layout. So pin layout, we have two kinds of pin. One is little bigger pin and one is smaller pin, so that we can have a better heat dissipation, and we have better air vent or something like that. And this is how all the IPMs are actually designed, so that we can avoid lot of heat dissipation or temperature rise during the operations. And we have 2 notch as well, which can be utilized for putting the heat sink very easily. That's the understanding they have. And you can see we have pin number 1 to 16 one side, and then 17 to 26 another side. Okay. Next is let's get into the electrical ratings or electrical characteristics. So any of the ICs other time we have seen, let us say we have a linear regulator or switching regulators, or we have like any MOSFETs or any microcontroller, any IC if you see, you will be getting a absolute maximum rating table. Okay, so absolute maximum rating table, this particular IPMs has two, three, like sections. One is inverter part. So inverter part is nothing but that IGBT part. So IGBT part, as you can see, the maximum rating that it will take up is 600 volts. So you have to make sure the DC voltage that is going to come up into the your P terminal, that should not exceed more than 6 volt, otherwise it will get damaged. Similar to that, we have continuous current rating which is up to 3 ampere maximum, and the pulse current which has to have less than 1 millisecond time, then only it can reach up to 18 amperes and no problem will be there. And the total power dissipation across the each IGBTs will be 8 watt. Okay, so this was all about inverter part, which is actually nothing but the IGBT terminals or IGBT parts. Coming back to the control part, so control part is nothing but the gate driver or something like that. So if you see, we have out U, out V, and out W to the ground. So maximum voltage will be boot plus 3, and boot voltage is nothing but your 618 volt. Okay, and we have low voltage power supply, which is going to be maximum 18 volt. That we have to understand very clearly. Coming back to input logic supply, that will be going up to 15 volt. Okay, so that is nothing but our PWM signal, which is going to come into high side drive, high side logic supply and low side logic supply. So that can take as high as 15 volt, but we will not be giving that one. We will be always sticking to, let's say, 3.3 volt logic or 5 volt logic. If you want to translate to higher voltage, then we can utilize translator in the middle. Coming back to the total system, so third section is total system. You can see the isolation voltage is 1000 volt, that is 1 kV is the isolation. So you can see isolation with a stand voltage applied between each pin and heatsink plate is 1000 volt. We have a power chip operating junction temperature range is having minus 40 degree centigrade to 150 degree centigrade maximum. So this was all about absolute maximum rating, but these are just absolute maximum rating which need not be operating conditions, because operating conditions will be little bit different, which will be much lesser than this. Okay, so this is not the operating condition that we have to understand. Coming back to the inverter part of electrical characteristics, let us get into test conditions. So as you can see, there are some test condition in that in inverter part. It is showing what is the VC saturation, that is collector to emitter. We have, this is my let us say IGBT. So this is my collector, this is my emitter, this is my gate. So the voltage between VCE, that is your saturation voltage once it starts working. Okay, so this is the place where we are taking, let's say, U phase, and this is the place where we are giving DC input. Okay, so once there is a gate driver present, then this will start working, and at that time this will reach into saturation mode. So that saturation voltage will be 2.15 volt. Okay, similar to that, we have a collector cutoff current which is just 250 microampere, and then diode forward voltage is just 1.7 volt maximum. So diode is where it is coming. Diode, here is the diode that is connected. So this is also called as forward diode, or freewheeling diode, something like that. Okay, let's get into inductive load switching time and energy. So inductive load, if you see, we have turn on time, turn off time, which is mentioned very clearly, that it has 275 nanosecond and 890 nanosecond, which is close to 1 microsecond. Okay, similar to that, we have turn on energy, switching energy just 18 microjoule. Okay, so that's the understanding we should have in our mind. Let us get into more information. So hope you have a good understanding about how things are working. Now they have given a switching time test circuit, like how much time it takes to switch on, switch off. So what we can do is, one of the lean pin, let's say lean U pin, we can take. Okay, and in that we can feed one PWM signal. Okay, so in that what will happen, all the other high drive logic supply, we can ground it. So all the high drive logic supply has been grounded. We apply VCC pin with 15 volt. Okay, so this is my PWM input that is coming here. Okay, now coming back to the boot pin. So boot pin, we have to connect let us say 15 volt here as well, and then or it must be greater than VCC, it is saying. So let us say we are going to put boot pin as 100 volt. Okay, Now, coming back to this high voltage drive and low voltage drive, so that is going to drive one of the pair of my IGBT, and here V bus is there. So let us say 100 volt, you can try to put it and check it. So just to testing purpose, you can test with even 100 volt, or let us say even 300 volt, you can apply. So there is an inductive load that is there, and we can see that whenever this PWM is going high, there will be a work, working here, and this is how there will be current that will be increasing. Okay, so as soon as it goes high, the current starts increasing. As soon as it goes low, it will start going down. So this is how the things will be there. And this is a DC link capacitor. You can put it, let us say, 1000 microfarad. Okay. Good. So this was all about test conditions. Now moving to the next part, which is there, my control part. So there are a lot of, like control part and bootstrap voltage or something like that. So let us say what is the VCC hysteresis? So that is minimum zero point 0.9 volt. So once it is high, then once it goes low, minimum 0.9 volt difference would be there. Then it will, then only it will change its state. Otherwise it won't change the state. Anyway, this is nothing to worry about. Coming back to the boot threshold, so boot threshold on is 9.5 volt minimum, and boot threshold off is 8.3 volt, 9.5 volt typical and 8.3 volt typical values. Okay, we just remove this so that you can see it clearly. So 8.3 volt. As you can see, bootstrap driver on resistance is 125 ohms. So the gate driver MOSFET is there, which is going to drive the IGBTs. So their on resistance is 125. Coming back to the logic input, so logic input, we have low level logic and high level logic. So as you can see, low level logic voltage in test condition, we can see we have 1.1 volt maximum, and high level logic is 1.8 volt maximum. Okay, coming back to high voltage, high logic level 1, that will be -1 microampere. So this is nothing to worry about. Let's get into the next page. Yes, this is very, very important. We have dead time and interlocking definition. So let us say we have low level logic PWM and high level logic PWM. So as it goes high, you can see here, then there is a dead time here inserted. Okay, so this is how it is working. Now it goes high, and then again, before the other one goes high, you can see there is a gap here. So this is kind of dead time again. Okay, so this is how it is actually working. So you can see this is my dead time. Whenever the other one is goes low, and it takes still time, it doesn't go high immediately. So that's the reason it is called as dead time. Understood? Coming back to the NTC thermistor, so we have NTC thermistor. So the value of NTC resistance at 25 degrees centigrade is 85 kilo ohm, and we have 100 R100, that is resistance at 100 degrees centigrade is 5388 ohm, that is 5.388 kilo ohm. So as my temperature is increasing, my resistance is decreasing, you can see. Okay, and we have beta constant, that is B constant is 4092 Kelvin. So if you want to have a like a value of resistance at temperature T, so you can utilize this particular formula to get the exact resistance of a particular temperature. So in ADC, while designing the circuit, we'll try to identify that as well. So what is the value of ADC that is red? So based on that, we'll be able to find out what is the resistance, and that resistance we can identify at what temperature it was based on this particular formula. Okay. So we have the temperature, we have beta constant, and we have R25, like resistance at 25 degrees centigrade. So at any temperature T, we can identify what is the resistance. So let us say we have a temperature of 50 degrees centigrade, put T equal to 50, you will be able, so you have to understand that this T must be in Kelvin. So 50 degrees centigrade, if you have to put, then you have to add 273.15 Kelvin, that you have to add in this. Okay. Okay, so that's done. So this is the graph for our NTC resistance versus temperature. So as you can see, as my temperature is increasing, my resistance is actually decreasing. Okay, so you can see NTC thermistor resistance is decreasing based on the temperature that is increasing. So that was all. Now let's go back to the application circuit. So application circuit is actually very important. We have to understand what are the different parts that need to be taken care while designing the circuit. Okay, so if any circuit, if you see, we have our controller part, which is my microcontroller, okay, MCU. So we have LU, NU, and LV. So these are actually PWMs, okay, not that. This U pair, V pair, and W pair. Okay, so that we have to understand. Next is, these are actually going to get into the LU and I mean lean U and H in U with a proper filter. So this is my filter circuit with RC combination. So during our design or in our implementation, we'll give you each and every values of that. But this is the architecture, this is the circuit understanding that we should always keep in mind, that we should have a like RC filter before sending it to our particular gate driver, I mean logic supply pins. Okay, so this is at the gate driver which will start driving based on the PWM that is coming here. Okay, coming back to the VCCU. So VCCU, as you can see, let us get into here. So we have a VCC supply here. So let's say we are giving it 15 volt through some DC output. So there is some DC output, okay, which is coming from, let's say, AC-DC converter, or let us say some switching regulator or some LDO. Anything is fine. Okay. So we have 15 volt that is coming to this pin, and this pin will be supplying the low level power supply for W, for V, and for U. Coming back to other parts, which is going to be temperature. So temperature, see, this is the place where we will be getting temperature output. So this NTC output can be taken out, and it can be given to our temperature monitoring device, that is nothing but some ADC, which will be trying to understand what is the value of temperature, and we can pull it up by some voltage, which is, let's say, 5 volt logic or 3.3 volt logic, based on the logic level that microcontroller is working on. So we'll do that as well in our design and details. And rest, what other pins is remaining? That's all, this is done. Coming back to right side. So in right side, we have V-boot pins. So V-boot for U, V, and W is there. Okay. So in V-boot pin, we have to supply a voltage with Zener diode, as you can see. Okay. Now coming back to the main supply, which is my DC input. So DC input is going to be, let us say, 300 volt. Okay. So that we'll see what is the voltage rating that we have to give here. So this DC voltage will be coming from, let's say, high voltage batteries, or maybe UPS or something like that. Otherwise, generally in home appliances or something like that, what we do is we have AC input. After, like, safety and protection and all those things, we'll put one bridge rectifier, and this bridge rectifier will rectify the output in like this form. So this bridge rectified output only is given as a input to this DC input with one bulk capacitor. This is also called as DC link capacitor. So DC link capacitor and one more filter capacitor, if you want, you can put it. So that's all. This is how it is put. Coming back to the motor driver. So motor driver, we have U output, V output, and W output. So those three phases are connected directly to the motor phase, which is U, V, and W. And next part is we have negative supply, which is NU, NV, and NW. So those are getting connected like this, and they are going to come up with a shunt resistor, which will be like helping us to monitor the current. Okay, so this is how it works. Measure of the application where we don't have a issue of costing or something, then each of the negative supply input will be having separate shunt resistor, and they will be going to go into the op-amp, or let's say current sense amplifier. Okay, so this current sense amplifier will try to give us a output voltage, and that output voltage can be sent to some microcontroller ADC or as external ADC to identify what is the current, being measured, or current being consumed in each of the IGBT terminals. Okay, so this was all about complete design. Now let's get into the next items. So as we can see, we have guidelines. So whenever you are designing with STMicroelectronics device, we have just after the schematic, we have guidelines. So that schematic which was just now explained, that can be very well understood by this particular guidelines. Each and every lines you can study, and you can see what is the values of my Zener diode or my capacitors or my like RC filters, and what should be their values and everything. Okay, so these guidelines you can refer. Otherwise, we have application note as well, which is relevant to this particular design, which is AN4043. So this, if you search in Google, then you will be able to get it. Now coming back to the most important part, which is called as recommended operating condition for this particular IPM. So in this particular IPM, what we can see is we have the voltage at P terminal, or between P to N terminal, that is nothing but like positive to ground terminal. So that is going to be between P and between the NU, NV and NW. So that it will be typically 300 volt. That's the reason I'm telling you all the time DC input will be around 300 volt. Maximum you can give 500 volt. Okay. So let us say we have a voltage at 85 volt AC to 265 volt AC. Okay. So after rectification, it will go into how much? 85 root 2 and 265 root 2. So 265 root 2 is going to go into around 375 volt. So it can be easily given, no problem. You don't have to reduce this particular voltage. So after bridge rectification, you will be having maximum at 375 volt. But general AC input is around 230 volts, so that will be close to around 320 or 300 volt. Coming back to the control supply voltage, so VCC, which will be generally used 15 volts. So we will be using one AC DC converter, or we will be having a power supply of close to 15 volt from some switching regulator or something like that. Generally, I have been using in several of my designs for my dishwashers or water pumps, or like motor drivers for different applications like compressors or robots or something like that. Coming back to high side bias voltage, so we have high side bias voltage which will be taking up minimum 11.5 volt and maximum 17 volt. So same 15 volt will be supplied to this as well. We have dead timing. So dead timing is minimum, like 1.5 microsecond we have to give in dead time. So that will be designed by the software person who will be designing the PWM signal to drive the gate drivers so that they can supply it to the IGBTs. We have PWM signal. So PWM signal, we have to make sure that the maximum frequency that can be applied as PWM signal will be 25 kilohertz. So as I told you, like HIN and LIN was there, which is high voltage logic input and or high side logic supply and low side logic supply. So their PWM signal for each one of them, like U, V and W, and here also U, V, W, the maximum frequency that we'll be using is 25 kilohertz. So generally I'll recommend you to use 10 kilohertz. That is more than enough for any of the applications. Moving to the next information, we have package information. So package, I have already told you, it has the like type C package outline. So it's nothing but like it is very eco-friendly, as well as very nicely designed to have very good environmental compliance, as well as very good heat dissipation as well. Next is this is all about packaging. Coming back to this mechanical data and all is there. So what is the size, what is the pin pitch, and everything is there. If you move to the next part, you can see when this particular IC was released. So as you can see in revision history, they have told that this IC was released in 2014, and they have been again modified in 2022. So this is nice to keep on going for low power application for different systems wherever there will be a requirement of IPM. Then at last we have the table of content. So if you directly want to jump at some particular place, let's say you want to see electrical characteristics or you want to see the application diagram, you can directly click here and you will be able to reach to that place. Alright guys, so hope you have a good understanding about one more IPM datasheet and what are the informations that is available inside a datasheet, and how to take out all those informations, let's say pin descriptions or pin functionalities, and what is the maximum voltage or current ratings that will be there applicable to each of the pins, and what is the block diagram of particular IPM, and if there are some example circuits that is given which can be always referred. So those are the things that you can always take care. At the same time, if you go into the product page of this particular device, then you will be seeing you have evaluation board. So in evaluation board, you will be getting a complete system design itself with my microcontroller part, my microcontroller part, and like other several I mean your IPM and other several parts, like let us say we have to have some op amps circuitry, or some like current sense amplifier, some comparators, all those things. So all those parameters you will be able to get in your evaluation board. At the same time, how to supply the power supply, let us say 15 volt is needed, or 5 volt is needed, 3.3 volt is needed, and we have to have a requirement of DC voltage which is 300 volt. So all those will be there available in our evaluation board. At the same time, what we'll do is, in our coming sessions, whatever I have designed in for like several of my projects, several of my practical examples, that will try to explain you to understand how you can take it forward for your design, in your own applications. So hope you do, you have enjoyed this particular session. If you do have any questions or any queries regarding this, you can put down your questions in the comment box. And if you are expecting something more, let's say some other ICs that you want me to explain you, or if you have a particular application requirement where you want to identify which IPM I should use, please put down your questions in the comment box and we shall be able to answer you out. Thank you.